Hello, class, and welcome to the final chapter of your syllabus. This is chapter 26 or topic 26. And in this chapter, we're going to talk about radioactivity. So, what is radioactivity? What it's for? Where does it come from? What are the harmful effects of radioactivity? And how we can safely use radioactivity in our daily lives. So, this first part is the introduction to this topic. So, we'll talk about what is radioactivity, where does it come from, and what do we use to detect radioactivity. Now let's look at the word radioactive for a second before we talk about radioactivity in general. There are two parts to the word radioactive. First is the word radio, and radio means to radiate, and that means to give out. And active means something that is done very frequently or very energetically. Some substances in the universe are radioactive. So, what does that mean for these substances? That means these substances give out something quite frequently. That's why they are active at giving out something from inside these substances. And this is why we call them radioactive. Now, what is the thing that they give out? What is the thing that they radiate? That is something that we will look at in part two. So, to give you a picture of what is radioactivity and what does a radioactive substance do, I have a simulation here. In this simulation, you can see carbon 14. Carbon 14 is an isotope of carbon, and carbon 14 is known to be radioactive. And in this simulation, we are only looking at the nucleus of the carbon 14. So that means there are no electrons shown here. We only see the protons and the neutrons. So carbon 14, what's so special about it? What makes it radioactive? Carbon 14 is unstable. So that means it needs to give out something. It needs to remove something from its nucleus in order for it to become stable. So I'll play the simulation and you will see what happens. Did you see what happened? This is carbon 14. It's unstable. What does it do to become stable? We will see. Right. So here, carbon 14, in order for it to become stable, it gives out two things. There's one thing here and another thing here, but don't worry about that. Just know that in order for it to become stable, it gives out radiation. And as a result of that, it becomes nitrogen 14, which is a much stabler substance or a much stabler nucleus or atom. So, as we established, some isotopes or some substances in this universe have an unstable nucleus. Now, over time, the unstable isotopes will break apart, okay, because they are unstable. And in this process, they will emit something that we call radiation and a particle. So you can see from this picture here, you have a radioactive atom, and this radioactive atom has an unstable nucleus. In order for it to become stable, it needs to break apart, and in this process, will give out radiation. So usually some sort of energy and some sort of particle. And what they are, we'll talk about in part two. This process where the unstable nucleus breaks apart, it's called radioactive decay. Okay, they break down. So that's why it's called a decay. So radioactive decay is the process by which the nucleus of an unstable atom splits up. So it breaks apart, and in this process, it gives out or it emits radiation. So emit is just another word for giving out. Two things that you need to know about this process is firstly, it's spontaneous. What does spontaneous mean? Spontaneous means it happens at a random time. You cannot predict when it happens. So it cannot be predicted exactly when it will break apart, when it will decay. And the second thing that you need to know about the radioactive decay process is that the radiation and the particle that is being given out, that is being emitted, goes out in a random direction. It can go forwards, backwards, northeast, southwest. We cannot tell where it will be shooting out to. Now, isotopes that give off radioactivity are said to be radioactive, and they are sometimes also known as radioisotopes. Now, radioactivity is invisible, has no smell, and makes no sound. In fact, it cannot be detected by any of our senses. Now, this can be dangerous because most radioactive substances give out harmful radiation. Some radiation are safe in some situation, but most radioactive substances, the radiation they give out are quite harmful. So, in order for us to be safe, we need to be able to detect this radiation. How do we do that? We do that by using a Geiger-Müller tube and a counter. So here in this picture, you have the Geiger-Müller tube, otherwise known as the GM tube. And usually a GM tube is connected to a counter, or otherwise known as a rate meter. And the counter or the rate meter basically just counts how many radiations is happening. So for example, 1 count, 2 count, and so on. The higher the count, the more radiation it's detecting. When radioactive particles enters the GM tube, it will make a clicking sound, and I'll show this in the video soon. So like I said, the counter for the GM tube counts the number of detected particle per minute. And the unit for radioactivity, there are a lot of different units for radioactivity, but for your syllabus, we say the unit as count or counts per minute, or sometimes even counts per second. Okay, for example, if you can have 10 counts, 15 counts, 11 counts, so that's just how many radiation that is being detected by the GM tube. You can also have the counts in terms of a certain period of time. Let's say you have 17 counts per minute, so that means every minute the GM tube is detecting 17 counts of radiation every single minute. And you can also have counts per second. Let's say you detected 115 counts per second. So that's every second your GM tube is detecting 115 radiation going into it. That is quite a high number of radiation going on. So this is a video that I found on YouTube, and this video is from the channel called Chemistry Demo Lab, Ohio State University. So let's watch this video. Okay, so I'll just narrate over this video. So on the right side, you can see the tube, and also it's attached to a counter. You have 3 substances. So this person will use the Geiger-Müller tube and check the radiation for the sodium chloride.
There aren't many ticks coming off of the NaCl.
And you will
NaI
see
is a different
there are
story.
not a lot of radiation being detected. Now, very important for GM tubes, every time it detects radiation, it will produce a beeping sound. You probably have heard it just now. Now she's gonna use the GM tube to the second substance, which is sodium iodide, and try to listen to the beeping sound coming from the GM tube.
NaI is a different story. Iodine has more radioactive isotopes than chlorine.
And then she's going to use it to detect radiation coming from uranyl nitrate. And this is a very radioactive substance. Let's see what happens.
Let's take a look at the uranium salt.
And you can see there are a lot of beeping sounds coming from the GM tube, telling you that this is quite a radioactive substance. Now, when you are using the GM tube, you will notice that even though when there is no radioactive substances nearby, when the GM tube is turned on, but you are not measuring anything, the counter still clicks or it's still producing a beeping sound, indicating that it has detected radiation even though there's no radioactive substances around it. So why does this happen? This happens because of something that's called background radiation. So, what is background radiation? This is the radioactivity given off by the things around us. So, some things around us give out a little bit of radiation, and that counts towards the background radiation. So, this can come from building materials, natural isotopes in rocks in the ground, and even from space, otherwise known as cosmic radiation. So you can see here, some of it comes from industrial objects or industrial materials. Some of it comes from medical equipment. 10% of it comes from cosmic rays, so the space outside of the Earth. 12% comes from the human body. 14% comes from rocks and the ground. And also 51%, and that's quite a big chunk, comes from radon and thoron, which is in the air around us. Very important to note that the background radiation is just a very small amount of radiation, and in normal situations, it's just harmless. It doesn't harm us that much. In fact, right now, sitting or lying down watching this video, there is background radiation all around you. So, very important when you are measuring the count rate of a radioactive source, make sure you subtract the background radiation count. Okay, so to summarize part one, we looked at what is radioactivity and where does it come from. Radioactivity or radiation comes from an isotope with an unstable nucleus. This unstable nucleus will break apart and in the process will emit radiation and a particle. And this is what we call as the radioactive decay. The process of radioactive decay is spontaneous. That means we cannot predict when it will happen. It could be 1 second from now, it could be 1 day from now, 1 year from now. We cannot tell. And when it gives out radiation, the radiation will go out to a random direction. We cannot predict whether it will go forward, backwards, or so on. Substances that give off radioactivity are said to be radioactive, and they are sometimes known as radioisotopes. In order to measure radioactivity, we use an instrument called the GM tube. And the GM tube is connected to a counter, and the counter basically counts how many radiation that is happening. The unit for radiation that you will use for the syllabus is counts, or counts per minute, or counts per second, or even sometimes known as the count rate. And also, finally, we looked at background radiation. So, background radiation is the radiation given off by the things around us. Background radiation isn't necessarily dangerous, it's a low amount of radiation that we are used to ever since we are born, and it's all around us. So, it comes from cosmic rays from space, from human body, from rocks, and from the air around us. In the next part of this chapter, which is part two, we are finally going to look at what is the emissions or the things that are being given out by the radioactive substances.